All right, it looks like this is all we're gonna have. You want me to be on the camera here?
Only if you want to be.
You want to angle me? All right, hello and welcome to the Master's Defense for Jaimie Ritchie right here. Jaimie and I have known each other since she was a wee babe freshman at UNM. She was part of the very first cohort of our Grand Challenge Water and Climate Science Communication Fellowship. She was mentored by one Heather Himmelberger way back in the day. And as soon as I met Jaimie, I knew I wanted to hire her. But the problem with Jaimie is everyone wants to hire her. So I was third in line. She first worked with Heather, then she worked with Mark Stone, then she worked at DBSA and Associates, then she worked with me. So it was a long time coming, but I'm so proud of her. Jaimie's one of our exemplar students. She was an excellent undergrad. She majored in civil engineering and also played the viola in
Or violin, yeah.
and the violin in the orchestra. And now as a master's student, she's been doing incredible work on understanding air quality analysis here in Albuquerque. She's built a lot of partnerships, particularly with the city of Albuquerque, with Patrick Hudson right here, her committee member. Also with the Air Quality Control Board, we've got Joe Galuski here, as well as other community groups who hopefully are logging in online. All right, so I introduced two of Jaimie's committee members. We have Patrick Hudson from the city, we have Joe Galuski from EPS, and we have Ricardo Gonzalez Pinzon from civil engineering.
And of course you.
And myself, I'm the chair. I'm Anjali. Jaimie's going to give about a 30-minute presentation today. After that, we will have questions from the public, from all of you, for 5 or 10 minutes. Then we'll kick everybody out, and our committee will have about an hour, maybe a little bit more, to ask Jaimie questions, and then we'll decide what her fate is. After that, you are invited to celebrate with us with cake around 4 o'clock. We'll be at the tables right here on the third floor. So come back if you wish. But without further ado, I'm going to hand it over to Jaimie to share her research with us. Go ahead.
All right. So the title is What Pollutants Are in My Air? Source Characterization and Temporal Variability of Outdoor Volatile Organic Compound Exposure in Albuquerque, New Mexico, USA. If you've ever driven south down Albuquerque, down I-25 from Albuquerque, you may have noticed a brown haze to the skyline. And it may have made you wonder, is the air here safe to breathe? How do we know if something is safe? We can assess the environmental risk. Risk is a function of hazard and exposure, where hazard is relative and it's about how dangerous a pollutant is relative to another. Ones that are more dangerous are more hazardous. There's also exposure, which is how much of a pollutant is present. Understanding risk allows us to then form regulations. And we have regulations in our air for 6 pollutants. These are pollutants where we know the health concerns and we know the risk. They're ozone, nitrogen dioxide, particulate matter, sulfur dioxide, carbon monoxide, and lead. And we can assess how dangerous our air is on a given day by looking at these pollutants and comparing them to our regulatory level. Using that regulatory level, we can then determine if the air quality is good, green, or if it's bad, and red, with our air quality index. Most of these pollutants are emitted. Nitrogen dioxide comes from car exhaust primarily. Particulate matter can come from many different things, including dust storms, and can be composed of many different things because that is a size designation. Then you also have like sulfur dioxide coming from sulfur things and everything like that. However, ozone is not directly emitted. Ozone is formed. It is formed through a reaction that involves nitrogen dioxide, one of those criteria pollutants that we just talked about, volatile organic compounds, or VOCs, and these two react in the presence of sunlight, or ultraviolet radiation, to produce ozone. Hang on a sec. What are VOCs? VOCs are carbon compounds that can be found in our air, and some of them can be hazardous, but not all of them are. They're all different. Some of them are carcinogenic, which means they can cause cancer. And there are no ambient outdoor air regulations in the US. We have indoor air regulations for some of these compounds. Other countries can have outdoor air regulations, but in the US, we do not. They can come from a variety of different sources, including human and natural sources. Anthropogenic sources include industrial processes, they come from cars. They can also show up in various products that you use in your everyday life, like your shampoo or different fragrances and flavorings in products that you use. They also are naturally emitted from plants. They might just come from the trees naturally on a given day, and then they're exacerbated during events such as wildfire, which might cause more and more hazardous ones to then be released into the air. So this is a picture of Albuquerque. We have I-25 and I-40 there, the railroad, and the dots are showing stationary anthropogenic VOC sources. So each of these represents a permitted pollution source, either industry or different things, gas stations. And so each of these is a permit source, and they are sized based on their VOC contribution. So bigger dots means that there's a larger VOC permit. And you can see different clusters, like especially around west side of I-25 and kind of in the south there by the railroad. And that area is called the South Valley. The South Valley is predominantly a Hispanic low-income community in Albuquerque. It is 34% Hispanic and 34% low income and 80% Hispanic, which is higher than the rest of Albuquerque. The area has a lot of industrial activity, also agricultural activity. You have traffic from the freeway there, rail traffic from the railroad, and also we have 3 Superfund sites in Albuquerque, all of which are kind of in the southern region, more or less nearby the South Valley. And so back in 2014, the South Valley of Albuquerque, different community groups filed a Title VI complaint against the City of Albuquerque Environmental Health Department, filed to the Environmental Protection Agency. Title VI prevents discrimination based on race. And so they submitted this complaint in 2014, and they ended up following it up with another complaint in 2024. They also advocated for a local rule called the Health, Environment, and Equity Impacts Rule, which was designed to restrict VOC emissions in what were designated as overburdened areas. The implementation of this rule was rather complex politically. The Air Quality Board got disbanded and there was a whole fiasco, but it did get passed and is now active. And so in response to the original 2014 complaint, the City of Albuquerque established the San Jose Special Purpose Monitoring Site in 2021. It's technically a trailer. It could be moved, but it's been in the same location since it started measuring in 2021. It's analyzing the EPA-regulated pollutants that I mentioned before, which are also measured at various other locations across Albuquerque. But what makes this site special is that it's measuring volatile organic compounds, these VOCs. It is the only site that is formal that is measuring VOCs in New Mexico. However, it's been measuring for the last 5 years. None of this data had previously been analyzed. This is where the trailer is in Albuquerque relative to these pollutant sources. You can see it's kind of in this general vicinity of the South Valley. That's a picture there of the trailer. And so my goal was to analyze the exposure, sources, and temporal variability of VOC concentrations in Albuquerque, and then to go and inform the community of these concentrations and tendencies. That goal, I have 3 primary objectives related to exposure, sources, and variability. So exposure, looking at how frequently are compounds measured and how do they compare nationally and to existing regulations. Under sources, I'm looking at what are the VOC source categories within Albuquerque based on our data. And variability, is there a temporal relationship between VOC sources, nitrogen dioxide, and ozone? And what is the dominant wind direction of sources? VOCs and nitrogen dioxide, when they react to form ozone, we expect ozone to be higher when more solar radiation is present, so middle of the day in the summer. And when it's higher, we often see nitrogen dioxide and VOCs dip as they are consumed in that reaction to produce ozone. But before we can look at that, we have to look at the data. So the trailer is analyzing VOCs each hour and continuously through the use of two different measurement devices. They are the autonomous gas chromatography flame ionization detector, or the GCFID, and then a quadrupole mass spectrometer, or the MS. And so these two instruments are measuring simultaneously, and I received the data from the EHD, aka Patrick sitting there, and was able to perform quality control on the data for the flame ionization detector. So each of these instruments has three components: an intake, a column, and a detector. The intake is basically taking the compounds from the air and gathering them together to concentrate them so they can then be measured. The column then reacts with the VOCs. You put the VOCs through the column, and it will react with different ones and cause some to come out sooner and others to be retained and come out later. So you're separating each of the compounds. Then they are detected either by the flame ionization detector, which is quite literally a flame that is burning them up, and you see a response from that that you can then measure, or the mass spectrometer, which is basically measuring the mass of these VOCs. And so how it works in our trailer is similar to this flow diagram here. It's a little complex, but we have the inlet on the left, and then it goes through the column, which is those plot circles, and then goes either to the flame ionization detector or the mass spectrometer. And so we have two separate FID machines, one that is measuring light compounds with C2C6, so carbon 2 to 6 carbon atoms, and then one that is measuring C6C12, so 6 to 12 carbon atoms, the heavier compounds. And on a given hour, so for the first hour, the FID will measure the light compounds, and the heavy compound airstream will go to the mass spectrometer. The following hour, it switches. The FID is measuring the heavy compounds, and the mass spectrometer is measuring the light ones. So it's kind of switching off, and then we process it using the proprietary software. So the benefit of the mass spectrometer is that it enables compound identification by identifying mass fragments, so it can tell what compound is what more clearly. However, it is prone to malfunction. It's primarily designed as a lab instrument, and in just the last year of 2025, the mass spectrometer in the trailer was down for about 6 months out of the year. The benefit of the FID is that it's a good field instrument and you can rely on it to continuously measure. However, it does not have the ability that the MS does to differentiate between these compounds. However, we are able to address that through validating the FID signal with the signal from the mass spectrometer. And so that's what I did. And so I used the calibration runs that are run every 4 days that has a suite of 75 compounds, and looked at the calibration run and each of the different peaks and looked at lining up the mass spectrometer signal with the FID signal. I used what was identified on the MS, for instance, as benzene. I aligned the peaks based on the time that they came out of the column and was able to identify benzene on the FID. Some of them were harder to identify. The MS had multiple compounds that were co-eluting, showing up at the same time. For instance, trichloroethane and 2,2,4-trimethylpentane. And so I labeled that one as ambiguous and excluded it because it wasn't clear which one of those we would be measuring on the FID. And so through that process, 34 compounds were able to be validated. I was only able to use the heavy airstream, the C6, C12, because the C2, C6 was determined not really readable on the MS. And so I only had a solid comparison for the heavier compounds. So then I had my data. Hooray! Then I was able to look at exposure. The first research question I had under this is what percentage of the time in 2025 are the compounds that can be reasonably measured by the FID measured at a level greater than the method detection limit, or the MDL? The second research question is what is the percentage difference between concentrations of individual VOCs in outdoor air in Albuquerque, New Mexico when compared to national levels and to existing regulations? So first off, we're looking at exposure. This graph is showing which compounds are, it's showing all 34 compounds in the middle. The left is showing how frequently they were detected in the last year. The right is a box plot showing the concentrations that they were detected at on a log scale. And they're ordered by which compounds are detected most frequently to least frequently. So our 5 most frequently detected compounds are here at the top: N-pentane, benzene, acetone, M&P-xylenes, and N-hexane. Overall, there were 11 compounds that were detected above the MDL in 2025, or more than 50% of the time in 2025. I have a little information about each of the compounds, its carcinogenicity level, or if it causes cancer, and then some of the health effects and sources. I'm not going to read through them because you can read if you want
Can I
to.
ask a quick clarification question, just to interpret, Jaimie? So, when you're saying MDL is method detection limit, right?
Yes.
Do you get that from the calibration, or how do you determine that specific?
That was given from the instrument. So the instrument had a specification of the method detection limit for each of the compounds that I was able to get from like the manufacturer company.
Gotcha, and then in that part, just because it's important to interpret as we continue, so if it is below the detection, you still took the number, or how did you handle that? That I don't understand.
Yeah, so the concentration box plots on the right, I'm only looking at the concentrations here that are above the method detection limit. So
all of those are.
yes, all of the box plots are concentrations that are above the detection limit. Otherwise, you have things like acrolein where it's detected 2% of the time, and you're not going to be able to see kind of the distribution because anything that's like under 50% detection is just going to show up as mostly below the detection limit and then a little tail. And so I did that to better be able to visualize it. Yeah, so speaking of concentration, we can look at what the concentration of these compounds were and which ones had the highest concentration. So this is the exposure piece of the hazard exposure equals risk, right? So it doesn't tell you which ones are dangerous. The ones that higher may not be dangerous, but they're showing up more often. So the ones that have the highest maximum measurement in the last year were acetone and hexachlorobutadiene. The ones that had the highest median concentration in the last year were acetone and butane, carbon tetrachloride, and hexachlorobutadiene. So acetone and hexachlorobutadiene are showing up in both of those. So VOCs are measured nationally in some locations. Specifically, they are measured for ozone formation. So they're required, spaces are required by the EPA to put in a VOC measurement site if they are determined to be in ozone non-attainment, which means they regularly have ozone levels that are above the national standard. The EPA only requires these in areas where the metropolitan statistical area has a population that is greater than 1 million. So the Albuquerque site is not a PAM site. It is a special purpose monitoring site that was put in outside of this program. We are not technically in non-attainment here in Albuquerque, and we also don't meet the population requirement. We're about 70,000 people short, so we're close, but not quite there. So there's 47 of these sites across the US. And so my question was, how are the levels of VOCs that we're measuring here in Albuquerque, how do they compare? And so first I looked at the median concentrations from each of these sites. So the median concentration in 2025 for each of the PAM sites, and I plotted that as the blue bar here, the range of median concentrations. The median concentration for this site in Albuquerque is the black dot. And so I also did a little bit of a comparison with how are we compared to this range. If it's blue, it's within the range. If there's a red triangle on the right, that means it's above the range. If there's a green triangle, that means it's below the range. So toluene was below the range. And toluene is not classifiable as carcinogenic and primarily comes from gas. There were 3 compounds that were above this range: isopropylbenzene, N-nonane, and N-propylbenzene. And all 3 of these compounds come primarily from petroleum refining and are industrial solvents. They also cause kind of more of the respiratory irritation kind of thing. So this is how our medians compare. Overall, they're pretty similar, but tend to be kind of on the higher side of what most PAM sites are seeing. So then I looked at maximum concentrations. Are we seeing days or instances where the maximum concentration is higher than the maximum concentrations that are being measured at PAM sites? And so the blue range here is showing the range of maximum concentrations for each of these compounds. Black dot is again this study. And so most of these are falling higher than most of the PAM sites. And then there's 7 that are showing up with a maximum that is higher than the total maximum. One thing to note with this is we're looking at hourly. Some of the PAM sites might be measuring an 8-hour average, and so their maximums might be lower because it's the maximum of an 8-hour average instead of the maximum in 1 hour. That said, these are the 7 compounds that are showing up above that: acetone, MNP-xylenes, N-decane, N-nonane, N-propylbenzene, O-xylene, and p-ethyltoluene. I talked about most of these had all the information in a previous slide. So overall, the maximums tend to be higher, but that could be a little skewed due to the fact that it's an hourly measurement. So next, I wanted to look at regulations. In terms of outdoor air regulations, as I said, we're not regulating any VOCs in the US in outdoor ambient air. However, there's one compound that is regulated in outdoor air in the EU. It's the only compound that they regulate as a VOC, and that's benzene. And they regulate it as an annual mean. So if the annual mean is higher than this value, then that's above the regulation. And that regulatory limit is 5 micrograms per cubic meter. My data is in parts per billion, so I converted it, and it's 1.565 parts per billion. And so I calculated the annual mean here in Albuquerque for benzene, and it's 0.186 parts per billion. And so benzene is overall 8.5 times below the EU regulation. So we're below that, so that's a good sign. And due to lack of other outdoor air regulations, I did a bit of a comparison to indoor air regulations. They are not directly applicable to this situation because they are designed for a working day rather than constant 24/7 exposure, and they also don't consider sensitive populations, children, elderly, people with health problems. So they're not directly applicable to this situation, but the goal is to get an idea of relative risk. Which of these compounds are more likely to be posing a higher risk than others? For instance, so first of all, let me introduce you to the plot a little bit. We have the compounds on the left. Each of those dots represents a different regulation type. We have OSHA, the Occupational Safety and Health Administration, the California version, NIOSH, and ACGIH. And so each of those regulations for the compounds that have them are shown by these dots. And then we have the same concentration box plot from before, again on a log scale. So they're well below the regulations. And then I ordered them by how close the median is to the regulation. So if they're closer to the top, that means the median was closer to the regulation than the ones that are near the bottom. So this means that acrolein, which is second down, is probably posing a higher risk than benzene, which is a couple lower. And so this gives us a relative idea of which compounds are more likely to be posing a health risk in Albuquerque than the others. And all the compounds, for the most part, are less than 1% of the indoor air regulations. So they're all 3 orders of magnitude below, which is a big difference. So we're well below them, but that's to be expected because they're not really designed for this. So now that we know that, let's look at sources. Where might these compounds be coming from? Because if we can understand where they're coming from, then we can take action to mitigate prominent sources that might be emitting. So my research question is, what source categories are identified based on correlations of VOC measurements as demonstrated through positive matrix factorization, or PMF? PMF is a tool. There is a downloadable version that is developed by the EPA, so you can download it from their website, which is what I used. And essentially what it does is identify sources based on correlations of these compounds. I've got a little analogy here. You can think of it. If you had a bunch of kids at a soda machine, they're not just going to get one flavor of soda. They're going to mix things because it's a soda machine. They can. And you don't know what they mixed, but you can take a sample of each of their drinks and you can measure things like the amount of sugar, the caramel coloring, the cola flavoring, the caffeine. And based on that, you can then, those are your variables, you can run positive matrix factorization, PMF, and you can get what are called factors. And each of these factors represents a different soda flavor. So one of them might have sugar, caramel color, cola flavoring, and caffeine. Another might have caramel color, cola flavoring, caffeine, but no sugar. And so those might be Coke and Diet Coke, respectively. And based on that, once you've identified your factors and what soda they compare to, you can then look at each kid's drink and see what the composition was. So this is what I'm doing, but the ingredients of my soda are VOCs. So VOCs are the variables that I'm measuring. And this graph is showing the factors, my soda flavors. In this case, my soda flavors are natural gas, industrial manufacturing, solvents and chemical processing, vehicle exhaust, and a chlorinated hydrocarbon background. And I was able to determine these based on literature and which compounds typically come from which sources. And so for natural gas, butane is almost completely coming from natural gas. And then acetane and pentane are also coming from natural gas. But pentane is also coming from industrial manufacturing and solvents and chemical processing. Vehicle exhaust is benzene, xylenes, and ethylbenzene, which is a standard profile of vehicle exhaust. Those are compounds we expect to come from the vehicle exhaust. And then a lot of the compounds are part of this background, but most of these compounds that are showing up in the background aren't showing up very often. So the detection of these compounds was usually closer to the 5% rather than being detected more often. And so this kind of shows the breakdown of each of these sources and which compounds are coming primarily from which sources. So thinking about these sources, natural gas, it can be influenced by heating your homes in the winter. We often use natural gas furnaces, things like that. It can also be from natural gas, oil and gas industry. There's evaporations of VOCs that happens, and so that can be contributing as well. Different rail activities can also contribute. Industrial manufacturing, lots of different industrial plants, chemical processing, same idea. Vehicle exhaust, probably primarily cars, like the freeway, but there's other factors that could be influencing. We have planes from the airport that might be going overhead. We also have the rail yard nearby. And then we have this chlorinated background that came out. It's not exactly a source, but it is present and it's showing up. And so this can be influenced by a couple of things. Chlorinated compounds can result from agriculture. Hazardous waste sites also can be off-gassing chlorinated compounds. And then we also have to keep in mind that the trailer is sitting in the parking lot of a local swimming pool. We use chlorine to clean our water and keep it from disinfect it. And so as that evaporates into the air, it might be reacting with things and causing this kind of chlorinated background to show up. And so to kind of figure out more about these, we can look at the temporal and wind patterns. I have two research questions here. Under temporal, to what extent is there a temporal relationship between VOC sources, nitrogen dioxide, and ozone across both diurnal and seasonal scales? And how does it reflect this chemistry of ozone formation? And then in terms of wind, what is the dominant wind direction of these VOC sources? Where do they tend to be coming in from? So this graph shows temporal variability. And so we have each of the seasons, winter, spring, summer, autumn, hour of the day for each of these subplots. My sources are on the top, and my criteria pollutants are there on the bottom. So my ozone and nitrogen dioxide are there on the bottom, and they're doing what we'd expect. Ozone is peaking in the middle of the day, while nitrogen dioxide is dipping. It's higher in the summer and lower in the winter. Based on UV, this makes sense. Our sources are definitely lower in the summer than they are in the winter for the most part. And they also seem to be peaking in the morning, dipping in the middle of the day, and then peaking again later in the day. And so it's showing this relationship which matches the nitrogen dioxide and is inverse to ozone, which makes sense based on the atmospheric reactions at play. The background source is not really, it's pretty flat, but that makes sense as a background source. It's generally present. Also, it's dominated by these chlorinated compounds, which are generally less reactive than some of the other compounds. They tend to be in the atmosphere for weeks as opposed to maybe a few hours. And so we expect them to be reacting less and show less of a relationship with ozone, which is what we are seeing. So that's diurnal. Now, wind direction. This is a fancy little plot where we have wind direction, which is done through polar coordinates, so north is at the top. And then wind speed is distance from the center. So a low wind speed is close to the center, and a high wind speed is farther from the center. And the purple area is just showing that that wind speed and wind direction were measured at the site. And then we have contribution, this color scale, which is showing us how much of a source is showing up at a given wind direction and wind speed. So a dark area is showing that less of the source is showing up from that wind speed and direction. And a light spot means that more of the source is showing up at that wind speed and direction. And so this can give us a little bit of an idea of what sources are. If it's showing up at a high wind speed, it's more likely that the source is farther away. If it's showing up at a low wind speed, it's more likely that the source is closer. And it also gives you that directionality. So for instance, we can look at natural gas and we can see that it's primarily showing up at really high wind speeds coming from the east. So coming from the east. And then there's also a little bit that's showing up more in the central area. So the east might be more some sort of oil and gas operation, whereas the center could be more like residential heating. We saw that it was much lower in the winter than it was in the summer, which supports that. It could also be different things like rail activities and stuff like that. So when we look at them all, we can see that solvents and chemical processing is also dominantly coming from the east at high wind directions, but is coming from the east at low wind speeds as well. Industrial manufacturing is coming predominantly from the south, is higher at low wind speeds, but also high at high wind speeds. And so kind of more this diffuse pattern shows that there's probably multiple sources and contributing factors that are playing into this, as opposed to one singular. The chlorinated hydrocarbon background is coming mostly from the northeast, but is also very diffuse, which makes sense as a background source. That said, we aren't seeing it come from the west or really strongly at the center, which we might expect with the pool site right there. So there might be other things that are contributing to that one. Vehicle exhaust is primarily very local, but also has a little bit at higher wind speeds. And one thing that might be influencing this is the fact that there's a nearby school that's going to have a lot of pickup and drop-off activities. We also have to consider that the rail yard is literally just a couple miles away and maybe contributing to high VOC levels that might get tied into this vehicle exhaust category. And it's so close that we would expect it to be showing up in this more localized area. So in terms of my research objectives, in terms of exposure, the VOCs were higher than the PAMS sites across the nation, but they were well below any existing regulations. They come from, in Albuquerque, natural gas, industrial manufacturing, solvents and chemical processing, vehicle emissions, and a chlorinated hydrocarbon background. And the sources are showing daily and seasonal variability and have these dominant wind directions. Some of the limitations of this is spatially, we can look at these wind direction plots, but we can't compare across Albuquerque or triangulate to try to find exact locations of these sources because we only have a singular measurement site. So there's only one location. This could potentially be improved by in the future moving the San Jose site. It would give you a location across Albuquerque. You would still have a temporal difference because it would be measuring a different year than your data from the San Jose area, but it would still give you an idea. Also, my analysis was restricted to the FID data for heavy compounds. I only analyzed 2025 because the instrument was recalibrated at the end of 2024, and so that data was cleaner. So this could be addressed by further investigation into the lightweight compounds and validating those with the MS, which can be done in conjunction with the chemistry department. And then further validation when the processed data from the mass spectrometer, which the chemistry department, aka Kurt over there, is doing. Once that's processed, then we can compare the levels that both the instruments are measuring and make sure we're seeing the same thing. So in conclusion, this project related VOC concentrations to nationwide concentrations and applied PMF to a new location. Also compared compounds to national levels. The median concentrations were roughly comparable, tended to be on the higher side, whereas the maximum concentrations were consistently higher. And this shows that VOCs can be high even in areas where ozone is technically in attainment. So it may not be giving us a complete picture of the US, just measuring in places of ozone non-attainment. So the research recommendations are to measure speciated VOCs from specific sources so that we know what each of these sources emits. Things like car exhaust, we know it's benzene, toluene, ethylbenzene, and xylenes. But some of these we might not fully know. And so if we can go and measure them and know what to expect a factor to look like, we can more accurately and reliably label these sources. Additionally, studying the compound hazard for each of these compounds in a greater depth so that we can then move toward having regulatory regulations for the more hazardous compounds. And then to measure VOCs in more locations, including areas that are not in ozone non-attainment, so that we get a better spatial representation of national concentrations. And also in these locations could perform source characterization, which then enables mitigation. In terms of the community impacts of this research, I want to talk a little bit about how it relates to local rules, my recommendations, and community engagement. The primary rule that this relates to is the HEI rule that I introduced before. This was initially established in 2024 to take effect in January of 2025. And the primary intention is to increase pollution control. So what it does is it requires new sources to use the best available control technology or BACT in areas of Albuquerque that are designated as disadvantaged based on this map. So this map, the blue highlight, shows areas that have been labeled as disadvantaged. And this rule applies to 15 VOCs. 8 of those 15 are within the 34 that I was able to validate from the trailer data. Those are acrolein, benzene, carbon tetrachloride, ethylbenzene, methylene chloride, naphthalene, toluene, and xylenes. There's others like formaldehyde and ethylene oxide that are not measured at the trailer. My recommendations to the Environmental Health Department moving forward is to work with a VOC specialist to manage the data and review data beyond the 2025 that I did to understand different changes in that data, to move the site to a new location so we have a better spatial understanding of Albuquerque, and then also to perform a full health risk assessment so that we know what the risk of these compounds that we're seeing. In terms of community engagement, I've been working with various community groups and presenting to them. So I presented to the Albuquerque-Bernalillo County Air Quality Control Board earlier this month. I've also been meeting and working with a couple of community groups throughout the course of this project. Los Jardines Institute and Mountain View Neighborhood Association were both involved in the original Title VI complaints to the EPA. So I've been talking to them. I've also been talking to the Air We Share, which was formerly EJ Air, which is a community group of multiple collaborators coming together in more or less the South Valley in Albuquerque. And then I've been working with the city of Albuquerque also throughout the process, receiving the data for them. And then I also wrote a letter to them with describing my results and presented my results at the end of April. And then I also provided a standard operating procedure document for them to be able to more easily process future data based on the process that I determined through this project. I've also been presenting at academic locations. Last December, I went to the Atmospheric Geophysical Union Conference in New Orleans and presented a poster there. I also got 3rd place in the Arid Poster Symposium and was a finalist for Lobo Bites, which is a 3-minute pitch competition to describe your research. No slides, no extras, just get up there. So final thoughts, understanding pollution sources can enable us to mitigate. And this study evaluated VOCs in Albuquerque to understand exposure, sources, and how they relate to local regulations. The results were then presented to community members. I would like to thank some of my funding sources, including the Southwest Environmental Finance Center, Center for Water and the Environment, and the UNM Honors Myers Fund. I'd like to thank my partners, the City of Albuquerque and the UNM Chemistry Department, my committee, Anjali, Patrick, Ricardo, and Joe, and then my family and friends for their support, my mom and dad, my partner Alex, and the entire Mulchandani lab. Thank you.